How y'all doing? This channel is going to be strictly for education purposes. Um, so right now I'm studying the organization of the body. This is physiology. The basis are there's fluid compartments and there's a solute distribution. That's in lecture one. Homeostasis, mechanism, and regulators. It's mass balance maintenance. Homeostasis is the main key factor in the beginning. The body components, as we know, start as a fertilized egg. There's division of that, and then the differentiation. I know that word. Differentiation. I know that. Yeah. Cells have a specific function. A group of cells are tissue. Tissue make muscles. Nah. There's the four. What is that? Muscle, nervous, connective, and the epithelium. Epithelium. Muscle, nervous, connective, and epithelium. Organs function for the body. The organ system has several organs that act together with a specific function. The skin is a barrier. The entry is respiratory and GI. Transport is CV and diffusion. GI and CV. And then the exit, which is the renal. Everything has fours. Example, the organ system, inside of it is the kidney and two ureters. U-R-E-T-E-R. Yes. And that's the renal or the urinary system, the exit. Skin, entry, transport, exit. The next major key factor is the fluid compartments. There's a plasma membrane. Inside of that, there's a ECF, ICF. These are key words. ECF, ICF. Equal distribution of solutes in that membrane, and 1/3 of it is the ECF. 2/3 is the ICF. Total fluid inside of it. High concentration of sodium, small concentrations of potassium are in the ECF. They're in the smaller part. But also proteins are important in the ECF. But they're completely different environments. An ATP comes into play. That's an enzyme. Water is a key component because total body water is 60%. There's also a math problem. 1/4 of the ECF equals intravascular space times X, 1/12. I think that's interesting. Math goes into it. Another key factor is their self-regulating mechanisms. Homeostasis and illness are intertwined. Key factors here are potassium, sodium, chloride, and calcium. We need to regulate the ECF, the smaller part of the plasma membrane, correct? There's a homeostatic control and reflex loop. The first trigger I know is the sensor. The second is the integration center, the brain set points. and I need to review that. That's obviously needs to be reviewed. Moving on, high salt diet. Let's say we're eating a bag of chips and such. On Monday, our diet and urine on levels is equal. Then the urine falls below on Wednesday, rises on Friday. During this week, where did the added sodium distribute? To the ECF, smaller portion. The volume of the water you drank affects that. Increased sodium, increased water. Concentration, constant. There's the vasculature. That's a key. Vasculature. Increased volume of blood, increased pressure within the cardiovascular. It's a self-regulating system maintaining an internal environment compatible with living cells and tissues. Excuse me. After this first lecture, there were practice questions. Question 1 is a cell in a steady state for K plus when is a cell in a steady state for K plus, which is potassium, positive, potassium. A cell is in a steady state for potassium when the potassium input into the cell is equal to the potassium output out of the cell. In other words, the rate of potassium ions entering the cell equal the rate of potassium ions leaving the cell. This steady state is maintained by a sodium-potassium pump, which pumps potassium into the cell and Na plus out of the cell, despite leakage. But some K plus will escape. By the way, that caused me to look at common ions and symbols in the homeostasis fluid compartments. We're dealing with sodium, potassium, chloride, calcium, magnesium, phosphate, and bicarbonate. And these symbols are Na. Sodium is Na, potassium K, chloride Cl, calcium Ca2, magnesium Mg2. I'm not even going to go over the other ones. They're just letters and numbers. Potassium, potassium. Sodium, potassium, chloride, calcium, and magnesium. NaKClCa2. So this says we're dealing with, in a steady state, K plus and Na plus. Na plus is sodium, K plus is potassium. We group these together then. Multiple choice question. Knowing this information, the extracellular potassium concentration exceeds the intracellular potassium concentration. Here we go, keywords, extracellular and intracellular. Intracellular is the ICF. That's intracellular fluid. The fluid inside the cells surrounds organelles, key factor, and cellular structures. Accounts for approximately 2/3 of the total body water. Now the ECF, that's the extracellular fluid, is the outside of the cells. It's approximately 1/3 of total body weight. ECF is the outside, ICF is the inside. Intravascular, key word. Intravascular fluid is the plasma in the blood vessels. Back to the question. Knowing that a cell is in a steady state for potassium when, answer, the amount of potassium entering the cell equals the amount of potassium leaving the cell per unit time. Multiple choice questions were A, extracellular concentration of potassium exceeds the intracellular concentration. B, the amount of potassium entering the cell equals the amount of potassium leaving the cell per unit time. Or C, the energy is used to maintain extracellular and intracellular potassium concentrations. The ECF potassium concentration. So the extra and the intra potassium, K plus, is equal. Question 2. Jim drank a bowl 300 ml. I know that's milliliters though. Of tomato soup for lunch. How would the sodium from the soup distribute into the ICF and the ECF compartment? Well, since sodium Na plus can barely cross cell membranes due to their lipid bilayer structure, almost all the sodium from the soup will distribute into the extracellular fluid compartment, the ECF. Particularly, this is in blood plasma and interstitial fluid. My personal notes. Lecture 1, homeostasis and fluid compartment. We know the common ions and symbols are Na, K, Cl, Ca2, Mg2. These ions are essential for various bodily functions, including maintaining the fluid balance. We'll also see symbols like H2O, pH, which is water and acidity or basicity levels. Maintaining the fluid balance includes regulating the pH levels, enabling the nerve impulses, and supporting the muscle contractions. pH, nerves, muscles. Also, common symbol is MEQ/L or MMOL/L. I saw the second one various times in the lecture. These symbols are for concentrations. They're milliequivalents or millimoles per liter. The lecture also included the millimoles per liter, so that's the MMOL/L. Intracellular, ICF, that's inside the cell, surrounds organelles. Circle that. Cellular structures, and it accounts for 2/3. 2/3 ICF, the intracellular fluid, which is in the intracellular fluid. Extracellular ECF, that's the extracellular fluid. And this fluid is outside the cell and approximately 1/3 of the total body weight. ICF is the inside, ECF is the outside. We're dealing with intravascular fluid. That's plasma in blood vessels. Interstitial fluid. Interstitial. Circle that. Surrounding cells and tissues. The inner. They got the intra in the plasma, in the blood, and the inter in the surrounding cells. Think of it like a house. The intracellular is the inside of the house, the cells. The extracellular is the outside of the house, surrounding the cells and the tissue. Well, whatever. I'm also studying exercise physiology, but it's interesting to see what comes into play and stuff. Regulation of homeostasis is the next key factor. When you're dealing with reflexes, there's a local response. Initiates a target cell, which responds. There's things called a gap junction For instance, calcium moving from cell 1 to cell 2, blood to the target cell. The next thing is an endocrine cell, which secretes a chemical, which goes into the blood, which goes to the target cell. You see? But there's a second process with a neuron, you could say, and there's a small space. They call it the synapse. SYNAPSE, circle that. This is a chemical, and it goes to the effector cell. So you need regulation, which has reflexes, with a response, which goes to the target cell, initiated by a gap junction, which takes, for instance, calcium from cell 1 to cell 2. For instance, an endocrine cell secreted a chemical which goes to the blood, which goes to the target cell. Number 3, reflex components. The sensor, the brain, and the effectors. They call the brain the integration center. That's the set point. For example, your body is supposed to be at 37 degrees Celsius, right? Go outside, it's cold, and then your body will like shiver to raise your temperature to a new set point, which is 40, something like that. But the sensor recognizes the stimulus. The integration center examines that input. Then the effector, the efferent path. That's the key word, efferent. EFFERENT, which designates a stimulus. Key factor. These are the reflex components: sensor, integration center, effectors, stimulus. Now there's an external change. The integration center, the brain, has a hypothalamus. HYPOTHALAMUS. Circle that. This hypothalamus set point is 37 degrees. Oh, nice. This is a peripheral and central thermal sensor. It has a set point which affects the effectors is the skeletal system, which is your muscle shivers. You shiver, and that's a vasoconstriction. Vasoconstriction. That's in the skin. Which results in a stimulus. The brain is the set point. Peripheral and central thermal sensors. Integration center, sensors, effectors, stimulus. This here is reflex components. Now there's a negative feedback loop. Say you have a stimulus and the receptor, your sensor, is an endocrine cell. Simple. There's a hormone secretion from that cell to the blood. Goes to a target cell, which is the response. That target cell has hormone receptors, which affects the skeletal muscle. Temperature, stimulus, cell A, cell B, cell C, etc. That's what I need to review. Because there's two parts. A, what I just said, stimulus, receptor, target cell, stimulus, sensor, response. And then I need to review part B. Positive feedback is a follicle stimulant hormone. If we take an endocrine cell that secretes a hormone to the target cell, then it goes to the next target cell. There's a dial up or down, never off. This includes tonic control and organ systems and other key factors. But that will be discussed in a later chapter. This is a vasoconstrictive, increased input, basal state, and decreased vasodilation. Such thing as a lumen keyword. Vasoconstriction lumen all right. Key factors in tonic control and the organ system. There's an increased output, which means the lumen is smaller. If I get this right, there's a basal state, which is the contraction. It's not completely open or completely closed. There's a decreased vasodilation, and that's closing. Increased input, lumen, basal state, contraction, decreased vasodilation, closing. Smooth muscles, what we're dealing with. It can hold a state of contraction for long periods. Internal variables, balance, input and output, negative feedback, variables corrected by bringing the body back to the initial set point. That's a reset. The brain and the heart always win. Different type of muscles, smooth muscle, skeletal muscle. Go back to the first part where we're talking about, seems like a lot of things are in fours. Muscle group, nervous, connective, and epithelium. Skeletal muscle, smooth muscle. That group. Now there's last key topic point. There's an antagonistic control. We just talked about a tonic control. This is pretty much like a dial up or a dial down, never off. And that's a vasoconstriction. That's tonic control. This is antagonistic control. The intrinsic heart rate is 100 beats per minute. Per se, athletes would go under a state of parasympathetic, which is slowing it down. slow down the heart rate is parasympathetic. Now, sympathetic is an increased heart rate, higher cardiac output, and that's the cardiovascular system. I gotta move, G. 3:15. Perfect.